Today I'm going to start by generating 50 synthetic data points for the step response of our system where there's two tanks in series. And then we're going to add a normally distributed error around each point with a standard deviation of 0.02. So the past couple videos we've been working on this same system, so I'm going to go ahead and draw that out. So we know that we have a Q1 going into our first tank, and that we have a Q2 leaving our first tank and going into our second tank. And we also know that we have a flow coming out of our second tank, but we're just going to call this our H2 since that's the response variable that we're trying to find. So there's a liquid level in each of these tanks, and where that liquid level sits is going to be our height value for the respective tanks. We have H1 and H2. So we also know that we have an H2 set point inside of our second tank. So we're trying to reach this H2 set point. So to manipulate our H2 set point, we are going to change the value of our Q1. So in the past couple problems, we've been talking about the transfer functions of our process. So we have already found that we have already found the transfer function for both parts of our process. So we know we have our Q1 going in, and we've already found our GP1, which is the transfer function of our first tank. We know we have a Q2 coming out of this and going through another transfer function, which is our GP2. And we're going to have our H2 coming out. And then we also know that we have a measurement device, which we can call GM. But in our specific problem, we are just saying that our GM is equal to 1. So we don't necessarily have to worry about this right now since our transfer function is just 1. So we're just going to multiply the value of 1. So we're still going to have the same product. So we are just going to continue to use the code that we've built in the past couple of videos since we're still working on the same problem. So if you want any detailed information on how I completed anything that's in this code, please go back into my playlist and we'll rewatch the videos before this one. So we are going to start out by creating a transfer function for our GP. So we're going to use our, we're going to name this our TF process. So this is the transfer function of our GP value that we were talking about on the whiteboard. So we're going to use the TF multiply function that we already created in this code. And we are going to multiply our Q1, Q2, and our Q2, H2 transfer functions together. And then we are going to run a simulation on this. So if we do our TF underscore process, we're going to start by running a step function on this. So if we execute, we can see that this gives us two arrays. Our first array will be all of our time values, and then our second array is going to be all of our H2 derivation values. So now we can tell our process what we want our experimental time values to be. So we are going to use t underscore exp for our experimental time values, and then we can use np.linspace to tell our code that we want to run our system from 0 to 15 seconds, and we want 50 data points. And to supply these values to our step function, we need to say that our t is equal to our t underscore exponent. So now we can see that this gives us 15 values, or it gives us 50 values between 0 and 15 for our times, and it gives us the corresponding H2 derivation value. So we can set this equal to an underscore for our t experimental since we already have those values from our linspace, and then we can do our H2 experimental values. And now we can plot this out. So I'm going to go over to my plot starter and I'm going to grab my make subplots. Our x in this case is going to be our t experimental values, and our y is going to be our H2 experimental values. And since we are using experimental data, we need to make sure that our mode is in markers and not a line. So if we execute this, we can see that all of our points are very uniform to each other. And with using experimental data, this most likely is not going to happen. So we're going to use a random number generator to create data points that are focused around where our data points are now, but that give them a little bit of ununiformity. So we're going to use our random number generator. We're going to set that equal to np.random state, I believe. And then we are going to give this a arbitrary number of 1, 2, 3. And now we can say that our H2 experimental values are equal to our random number generator dot, we want a normal distribution, and we need to set our initial location equal to our H2 experimental values, since we do want our random numbers to slightly look like what we have now. And then we need to assign our scale, which is our standard deviation, and we are going to set this equal to 0.02. And then we can rerun our plot, and we can see that we do have some randomness in our data points now. They're not in an exact line. So now we're going to fit the data that we just found by using a first order plus time delay model. So to start, I'm going to draw out the system that we've been working with. So we know that we have our we have our GP. So that's our process. And we know that we have some GM, but that in our case, our GM is equal to 1. And now we want to add a controller into our system. So this is going to be our GC value. And we know that we need some plus or minus signal going into our controller. So for our GC, we're going to use a PI controller. And so for a PI controller, we know the equation is KC, or our system gain times 1 plus 1 over tau I S. And now we can fit this system, we can represent this system by a first order exponential function. So we're going to have a graph of our first order exponential function. So it looks kind of like that. So the equation for this first order function is going to be our gain times 1 minus the exponential of our time over our tau. And we can see that we have this little bit of dead space at the front. So if we move our graph over to not include our dead space, it's going to look something like this. And our dead space here at the beginning is going to be equal to our theta. And now we can see that our equation is going to become our gain, our Kc, times 1 minus the exponential of our time times our theta, or our dead space at the front, divided by our tau. Okay, so now we can define a function for our FOPTD. So we can use FOPTD of a vector of variables. So inside this vector, we're going to have our variables k, tau, and theta. Set this equal to our vector. And then from what we found on the whiteboard, we know that we can find our FOPTD by our gain times 1 minus the exponential of our negative time experimental values minus our theta value divided by our tau. So we can just use some arbitrary constant y to set this equal to it. So we're going to have k times 1 minus the exponential of negative t experimental minus our theta, and then divided by our tau. So now we want to return, and we're going to use np.where. So when our t experimental values are less than theta, so that means that we would be inside of our dead time, we want to output a 0, so our our graph has no slope. And then if our t experimental values are above theta, we're going to return our y. So now we can make guesses for the variable of vectors that we had. So we're going to call this vguess. And then for k, it seems like our system reaches a high point of about 2. So we are going to guess 2 for our k. For our tau, it seems like our system becomes constant somewhere around like 4. So we're going to guess 4. And then for our theta, our dead time seems to end right around 1. So we're going to guess that. And like I said, those are all just guesses. They do not have to be perfect. So now we can define a function for our sum squared error, and we're going to use the same vector of variables. And then for our sum squared error, we know that we need to use our FOPTD model of our variables. But we know that our FOPTD model is just going to give us the difference between them. It's not going to include our original H2 experimental value. So we need to subtract our FOPTD model from our H2 experimental values. And then if we think about this, we know that we're going to get positive and negative values from this equation. So we need to make sure that we square it so each positive and negative difference has the same effect on our system. So then we can return the sum of this and it'll give us our sum squared error. And one last thing, we are going to try to minimize our sum squared error to give us the best graph that we can get. So we're going to use minimize, and then we need to tell it that we're looking at our sum squared error function, and we need to provide it with our initial guesses of our system. So we can see that we reach the most stable we can at our k is equal to 2.06, our tau equal to 3.55, and our theta is equal to 8.6 to the negative first, so that would be 0.86. So now we can set this equal to our result, so we can plot this out. So we are going to plot this line compared to our original plot that we just did. I'm going to copy and paste this down here. So we're going to leave this one the same, but then we are also going to have another plot that our y values are now going to be our FOPTD of our result, and then we're going to put .x since those are the values that we want, and then we're going to do our mode is equal to lines instead of markers. So now we can see that our system is passing through as many data points as possible, and our line is now following the curve of our markers. Okay, so now we can find the ITAE controller gain and the rest time for API controller. So to start, we are going to unpack our result.x into our values for each of our variables. So our k, our tau, and our theta. Since it gave us those exact values, we might as well use them. And now we can find our book gives us this information over here. So we can find our KC by finding our y and then dividing that by our k. And it also gives us our y equation, which is a times theta divided by tau to the power of b. And it gives us our a and b variables up here. So we can plug this in. So we can say that our KC is equal to so we have a, which is 0.586 plus, and then we have our theta divided by our tau, and then this is to the power of our b, which is negative 0.916, and then we need to divide this whole thing by k to find our KC. So if we look at our KC value, we can see that it's about 2.06-ish. And then we can also find tau from this equation that our book gives us down here, which is we can find our tau I, which is our tau divided by our tau I is equal to a plus b times theta over tau. So we can say that our tau I is going to be divided by, or is equal to, our tau divided by our A, which in this case is 1.03, plus our, or we're going to subtract since we have a negative number. We have 0.156 given for B, and then this is going to be multiplied by our theta divided by our tau. So now we can look at our tau I value. And our tau I is going to be around 3.58. So that is our AE gain and our rest time. So now we are going to go ahead and set our tau D equal to 0. So we can find the system for our PI controller instead of using a PID controller like we did last time. So if we run all of our code, we can see that in our graph here, so when our Kc and our tau I are equal to the values that we just found, this is going to be the response of our system when we change those values. And then the last thing we are going to look at is our crossover frequency and our phase margin now. So we actually can look at this graph of our phase and we can see that our system does not cross 180, or maybe we just are not going far enough. So if I change, no, I think this is the entire plot of our system. So this is the entire plot of our system. So we can see that our phase lag never crosses negative 180 degrees, which means that we don't have a crossover frequency. And this means that our system should never reach an unstable state. And then to find our phase margin, we need to find where our decibel equals 0 on this graph. And we can see that that is about around 1. So then if we go down around 1 radian per second is where our decibels equals 0. Yeah, it's around 1. So if we find 1 radian per second on our phase graph, we can see that our phase value is going to be around negative 140 degrees. So that means that we have over 40 degrees, or no, not over, but we have a little under 40 degrees before our phase would cross 180. But I don't think it does in this case, so we are not at risk of our system becoming unstable. Thanks for watching.